Hello, I welcome you all in this presentation related with the subject failure analysis and prevention. Uh, we are talking about the general procedure of the failure analysis under this subject, and under the failure analysis, under the general procedure for the failure analysis, we have talked about the collection of the background information, preliminary examination of the failed component, non-destructive testing, destructive testing of the failed component, and selection, preservation and cleaning, sectioning of the samples from the failed component. And now we are talking about the macroscopy of the fracture surfaces. So, the macroscopy of the fracture surface, which is carried out using the naked eye or the low magnification lenses or stereoscopic microscope, or maybe scanning electron microscope also below the 100 magnification. And whenever macroscopy is carried out, it helps to gather lot of information about the failure, which may be about like where the location where from failure was triggered or failure was initiated, the direction in which the fracture growth took place, means the crack growth direction can also be identified, and the kind of the loading conditions, means it is the tensile load, the bending load, or the shear load. And then we can also identify the kind of the stress state of the stress state in which failure has taken place, whether the failure has occurred under the plane stress condition or the plane strain conditions. So, likewise we have talked about some of the features like how to identify whether the failure is ductile or the brittle based on the macroscopic deformation in the material or the failed component. Now we will be seeing in this presentation few additional features related to the macroscopy of the fracture surfaces, and under this one is the beach marks if they are present in the failed component. So, to understand these beach marks, we need to see is let us take this is the shaft which is under the continuous tension and compression during the operation due to the continuous rotation, and somewhere the crack is initiated due to the prolonged application of the loading, and then crack grows. So, the growth of the crack will be occurring. So, the crack will be initiating somewhere. This is the first stage of the crack initiation. Thereafter, its growth. The crack will continue to grow until it reaches to certain stage where the load resisting cross sectional area or the left out cross sectional area is such that it is not able to take the service load anymore. So, that forms the third stage, and in between when the continuous growth of the crack takes place forms the second stage of the fatigue fracture, because the load is nature of the load is continuously changing here from tension to compression, and similarly similar kind of things can happen when the load is fluctuating, like say from tension to tension between certain values of like say 25 MPa to 250 MPa. Then similar kind of things will happen where somewhere crack will nucleate and then it will grow, and during the growth the crack the load resisting cross sectional area will keep on reducing, and then sudden fracture in third stage. So, third stage, second stage and the first stage of the crack nucleation. So, if we see both these cross section, means that the cross section or the failed fracture surface of both these components, then what we will observe, like one location where the crack has initiated, that will offer us the typical morphology which will be completely different from the remaining portion. So, this site whether we have some stress razor at this location, or even if the component was smooth, then due to the localized slip some kind of the crack was created after the prolonged application of the load, and once the crack has been nucleated it will be growing. So, the growth of the crack results in the formation of the concentric circle, and the center of these circles will be the location where from it has initiated. So, if we see all these concentric circles will have their center at the location where from it has initiated. So, these concentric circles are similar to the beach marks, and these indicate that how far or up to what extent there has been the second stage of the fatigue fracture. So, basically these concentric circles or the beach marks indicate the second stage of the fatigue fracture. And thereafter you see the load resisting cross sectional area is reduced to such an extent that it does not it is not able to take the load. So, the overload fracture will be occurring in the remaining portion. So, the third stage will be corresponding to the overload fracture. Now, this overload fracture can be ductile type or can be brittle type as per the nature of the material. So, ductile means this portion will have lot of dimples, that is the microscopic mechanism of the fracture, or it can have the cleavage facets, that is the another microscopic mechanism of the brittle fracture. So, so there are three stages, and it will be indicating how far particular stage was present. So, this is the first stage, this corresponds to the second stage, and this corresponds to the third stage. This is the case when the load is unidirectional. In this case, the crack is growing from one direction only, but there can be other situations also where, like say one simple rod is subjected to the bending in both the directions. In that case, the crack may nucleate from one side as well as from other side, and then in that case crack will be growing from the both the sides. And if that is the case, if the crack is growing from both the sides, then it will offer us the different kind of the surface morphology on the fracture surface. So, the case where the crack is initiating both the sides of the cross section. So, in that case, this is one stage for one side of the crack, and this is also first stage for another side of the crack, and then it will be growing in concentric circle manners like this, and it will be growing like this and from another side, and both and these concentric circles will be representing the second stage growth, and the center of both and the center of the concentric circles in both the cases will be the location of the location where from the crack was initiated. So, this is the first stage, this is the second stage, and the third stage is common for both type of fracture. So, this will be corresponding to the third stage. So, when the crack from both the sides grows to such an extent that load resisting cross sectional area at the center is reduced to such an extent that it cannot take the load anymore, and then the sudden fracture will be occurring, which is called overload fracture. And overload fracture can be ductile or brittle, as means it can be through the dimple mechanism or through the cleavage facets formation. So, it can be ductile and brittle in terms of the mechanisms. So, this is what has been shown in both these diagrams. This is the initiation site, and the remaining one is showing the beach marks. These are not very clear in this case, but these are very clear in this case where the crack is starting from both the sides, and then so this is the second case where the crack is growing from both the sides, and finally the third stage fracture is occurring at the center. And in this case, the crack is starting from one side and then it is growing, and thereafter third stage fracture is taking place. So, this is the overload or overstress fracture, and this is this is what we can say the zone which has been formed due to the growth of the crack. So if it takes over a long period of time, then obviously the surface which was formed due to the crack growth can get oxidized and it can become dull also. So, for example, if there is this crack was formed long back and it has taken very long time to cause the sudden fracture, then all the surface may get oxidized. So, we need to understand this aspect from another perspective, like 10 to 15% of the fatigue life goes in creation of the or creation or nucleation of the crack, and remaining like say 70 to 80% of the fatigue life goes in the steady growth of crack, and the third stage is the overload fracture, like very limited time, it takes like 5% or so of the fatigue life, or sometimes it is very quick. So, a third stage does not take much time, but most of the portion goes portion of the fatigue life goes in the second stage of the fatigue fracture, and since it is a very long time, means fatigue life which may be like in years, and where crack is growing gradually. So, the surface which has been formed due to the growth of crack will get oxidized and it will become dull. So, that is why what we will be seeing, that the location where crack was initiated and the fracture surface which has grown during the steady growth of the crack in second stage, that may become dull over a period of time, and then certain then the zone which has failed in catastrophic manner due to the overstressing or overloading, that of course will be the bright and the shining as compared to the first stage and the second stage of the fatigue fracture. So, these are the beach marks which indicate that the fracture has occurred under the cyclic load conditions 1, and the how far the contribution of the second stage of the fatigue fracture was, and what was the portion which has failed under the third stage of the fracture, where from crack has nucleated and in which direction it has grown. All that can be seen from these beach marks. Another important thing is the beach marks indicate lot of information, like the beach marks can be very close to each other, and these beach or they can be widely spaced, or they can be of the varying spaced, like say. So, the spacing between the beach marks indicate that the loading conditions have been fluctuating, and if the spacing is constant, then that will indicate that the fluctuation of the load is constant. If the spacing between the beach mark is changing, then that will indicate that load magnitude during the cyclic loading is also changing. So, the load fluctuation, extent of load fluctuation is also indicated by the spacing between the beach marks. Usually the spacing is close in the beginning of the second stage, and the spacing will keep on increasing as the time grows in the second stage of the failure. The another one is the fracture of a sample occurring due to the high temperature exposure. We know that that when a component is subjected to the constant load P, say this is the tensile load at a high temperature, say the temperature exposure temperature is high, about like say the 0.5 to 0.6 times of the melting point. The Tm is the melting point in the Kelvin. So, with such a high temperature exposure at a constant load results in the continuous increase in the length of the sample, which we quantify in terms of the strain. So, a strain, if that we can say as a creep strain, creep strain increases as a function of time at a high temperature. So, there is a continuous increase in length in this situation, or there is a continuous change in dimension of the component during the exposure at a high temperature. Depending upon the load and temperature conditions, the strain variation as a function of time is observed normally in this way, where we have a stage 1, stage 2 and stage 3. So, the stage 1 corresponds to the decreasing rate of the creep strain, stage 2 involves the constant rate of the increase in creep strain, and increasing creep strain as a function of the increasing rate of the creep strain as a function of the time. So, basically slope of the curve indicates the creep rate, the strain is the quantity. So, as soon as our the creep strain exceeds the acceptable limit, we say that the component life is over, now it needs to be rejected, or there may be another option that we may allow the change in dimensions until the complete fracture takes place, which is termed as rupture stress. rupture in case of the creep. So, this is the case when the fracture takes place. So, the creep experiences the various phenomena in course of the creep life. So, in the initial stage, what we see that the work hardening effect is dominating over the recovery, which is leading to the softening of the material. So, here work hardening dominates, that is why creep rate is decreasing, and here work hardening is balanced by almost the recovery. So, that is why the creep rate is almost constant, and the second stage recovery is softening and work hardening is increasing, is strengthening the material. So, when the recovery dominates, material is softened and the rate of the creep increases rapidly. Another mechanism here is the grain boundary sliding. So, the grain boundary sliding leads to the situation of the separation of the grains from each other. Like say this is the component and it is made of the number of grains like this. So, since at a high temperature or above the equicohesive temperature, the grain boundaries are weakened significantly, and that is why the grains start to move with respect to each other, and that results in the void formation between the grains. So, like say this is one grain and this is another grain, and so when the one grain moves with respect to the another grain, some void is created, and this void formation leads to the creation of the space between the grains. So, when the number of the voids are formed due to the relative movement between the grains, a lot of voids are formed, and subsequently their coalescence leads to the reduction in load resisting cross sectional area, and subsequently fracture takes place. So, this diagram typically shows the location near the fracture surface of the component subjected to the creep. So, if the component fracture is occurring at this location, then we will see lot of circumferential cracks, where due to the grain boundary sliding the grains have separated and leading to the formation of the lot of circumferential cracks. Mostly these cracks are localized near the fracture surface, and their numbers will be decreasing on moving away from the fracture surface. So, such kind of circumferential cracks are attributed to the separation of the grains, and this is what can be seen typically in this diagram, where lot of cracks all around the circumference are present, and this is the typical indicative of the stress rupture at which means the fracture of the component at elevated temperature. Another possibility is that at high temperature material may show the necking to the point where reduction in cross sectional area is almost 100%. So, here the significant reduction in cross sectional area, and eventually due to the overloading fracture takes place. So, this is also common phenomena. If the material is strong and grain boundary sliding is resisted, then continuous creep can lead to the significant reduction in cross sectional area, and which eventually will be leading to the fracture with the almost 99 to 100% reduction in cross sectional area of the component. So, as per the case, there may be lot of circumferential cracks, or the reduction in cross sectional area may be above 98 or 99% if the material is resisting the grain boundary sliding. So, this is these are the macrographs showing the lot of the cracks, and as I have said that due to the relative movement due to the grain boundary sliding, a lot of voids are formed at the grain boundaries, and that is why this kind of fracture also becomes the intergranular fracture. I will talk about the intergranular and transgranular fracture subsequently when we will be talking about the microscopy of the fracture surfaces. The another type of the fracture which occurs at a high temperature, especially the components or the systems which are subjected to the internal pressure, and they are exposed to the high temperature, like the boiler tubes, the boiler tubes having the hot gases being under pressure being passed through the tubes. So, at a high temperature, continuous internal pressure will be leading to the action internal pressure will be applying the force on the wall of the tube, and at a high temperature will be leading to the continuous increase in the wall thickness, maybe it may be localized also, and this high temperature actually degrades the material properties. It may cause the spheroidization of the steel, and which may lead to the softening of the steel under the softened conditions under the pressure. It may lead to the localized bulging or the change in dimension, and then thinning can take place. So, such kind of thinning will be leading to the thinning under the internal pressure. When the thinning crosses the limit under the effect of internal pressure, bursting of the tube takes place. So, this bursting of the tube happens in typical form, which is called I shape fracture. The fracture is of the I shape. So, this is one typical, these are the two diagrams which are showing that this fracture morphology is the similar to the shape of the eye, and this is also similar to the shape of eye, indicating that high temperature, that this kind of the morphology of the fracture indicates that the tube has been subjected to the high temperature, and because of the thinning, the bursting of the tube has taken place. So, this is another high temperature fracture. Here the fracture is occurring due to the thinning, and this primarily happens due to the degradation in mechanical properties due to the instability of the microstructure at a high temperature, and that microstructural instability primarily observed in form of the spheroidization of the steel. Then we know that whenever the component is produced by casting, so for the cleaning purpose we do the sand blasting, shot blasting. Sometimes for improving the fatigue life of the component also the shot blasting and the shot pinning is carried out. So, this kind of the cracks when the component is subjected to the cyclic loading also shows certain types of the crack, and which happens due to the localized slip phenomena at the surface. So, the some of the cracks which are very tight, very close, may be difficult to be detected under the NDT. So, if such kind of the cracks are present, then they indicate the possibility of occurrence or development of such kind of cracks under the cyclic loading, or the component has been subjected to the shot pinning, or the component has been subjected to the inappropriate heat treatment like quenching, because in these cases what happens in the case of the shot pinning, the shots will be directed onto the surface continuously, and the material is not able to absorb those shocks, is not able to deform enough, then it will be forming the cracks, and the continuous application of the shocks will be leading to the closing of these cracks also. So, these will be very tight and closed kind of the cracks. Similarly, such kind of the cracks are also formed when the component is subjected to the quenching, wherein when the component is subjected to the quenching, especially through section hardening, this leads to the increase in hardness of the steel, especially by the martensitic transformation, and when such kind of the martensite is formed, this is accompanied with the development of the tensile residual stresses also. So, the combination of the increased hardness due to the martensite, presence of tensile stresses, this leads to the development of the fine quench cracks. So, the tight closed cracks indicate the possibility of the fatigue fracture or the cyclic loading on the component development, or the quench cracks or the short pinning. So, if these are present, we need to really explore that if the component has been subjected to the cyclic loading or not, or it has been subjected to the heat treatment like the quenching, or if it has been short pinned. So, so according to the way by which material has been processed during the manufacturing, or the material has been used during the service, we can identify the kind of the loading was there, or if there was a problem with the manufacturing procedure with regard to the short pinning or the quench crack formation. So, these close cracks are you see difficult to be checked by the naked eye, and they need very careful observation for this purpose. Now, we know that whenever the fracture occurs, so the fracture here also like in case of the fatigue, what we have seen, the nucleation, then continuous growth in the second stage, the continuous growth of crack in second stage, and then sudden fracture in third stage. Similarly, the cast iron fails in different way than the common mild steel. So, depending upon the kind of the metal under the extra and the kind of load under which the failure is taking place, the different kind of the fracture surfaces are created, and those fracture surfaces offer the unique features with regard to the shade, with regard to the texture, color, and the roughness. So, we can gather a lot of information from the roughness variation present in the fracture surface, the kind of the texture which is there in, or the kind of the shade or the brightness or the dullness which is present on the fracture surface. So, the color, the roughness, the texture, or their variation will indicate that what is going on and up to what extent which type of mechanism was involved. So, all the idea about those kind of things can be taken from such kind of features which are present onto the fracture surface. Like say this is one typical one where like say this zone shows the one color, this is the another color, and this is the third color, and as per the case it will be indicating the variety of the features. So, we will be talking in detail about the color, roughness, and the kind of the surface texture which is there with the different type of the fracture surfaces in the subsequent slides. The chevron marks or the radial marks, these are the two features which are used to indicate the direction in which the crack has grown. Chevron marks are basically on the fracture surface, they are of the V shape. Normally, the tip of the V indicates the direction opposite to that of the crack growth. So, here if we see all these the tips are pointing towards the direction of the direction where from the crack has initiated, and the growth direction is opposite to this one. So, here the growth direction will be this one, and this will be indicating the direction where from it has initiated. So, these are the general conventions. There may be exceptions also in some of the cases where the chevron marks, the tip of the chevron marks indicates just the reverse phenomena. So, basically the chevron marks, these points towards the initiation site. So, if the chevron marks are oriented like this, then they will be pointing towards the initiation site. This is the normal general understanding, but in exceptional cases, in some of the cases also, the chevron marks will be pointing towards the end fracture zone, but that happens very rarely. And similarly, here what we can see, these are the chevron marks. Here they are of the different morphology. Here chevron marks are going like this. Okay. So, they are pointing towards the initiation site. This is the initiation site, and the crack has grown in direction opposite to that of. So, crack propagation direction and the initiation site, these are the two indications which are given by the chevron marks. So, here we can see this is the initiation site, and the chevron marks are being shown like this inverted V shape. So, these inverted V shapes, in case of the thin and thick sections, it can be of the different morphologies, but this will be pointing the V, inverted V will be pointing, or the tip of the chevron marks will be pointing towards the crack initiation, and they will be indicating the direction opposite to the, means the tip will be indicating direction opposite to that of the crack growth. So, arrows indicate the point here, this is the arrow which is indicating the direction where from the failure has been triggered or initiated, and this is the direction in which it has grown. So, about this I have already talked, that when the fracture is ductile in nature, we will see lot of deformation and the suppression, and when the fracture is brittle, we will be able to observe many small pieces of the failed component, just like a cast iron. When we drop the cast iron from a height which is of thin sections, it will break into the fine pieces. So, the like glass fracture is also brittle fracture. So, the cast iron also fails in the similar manner. We will see a lot of the deformation in the case of the ductile fractures as compared to that of the brittle fracture. And now these are the radial marks. The radial mark feature are poor. Here we can see the chevron marks are here. We can see lot of chevron marks, and all these are pointing towards the initiation site. This is the fracture initiation site. But here if we see the radial marks, these are the weak radial marks which are present, and they will be indicating towards the so these are the indicating the direction in which the crack is the growing, and their center will be towards the initiation site. Now, I will summarize this presentation here. I have talked about the few macroscopic features and what inferences can be obtained about the loading conditions and the technical information about the conditions under which fracture has taken place, and these features were primarily like the beach marks or the circumferential crack in the component which failed under the stress rupture conditions, which failed in stress rupture manner, and also the chevron marks and the radial marks present on the fracture surface. So, what kind of inferences can be obtained from these features present on the fracture surface? Thank you for your attention.